So mass transfer coefficient. So we said that we are defining our flux Na, and that is equals to, let it be like we have defined few cases, and based on those cases we have defined it. Now what if those specific cases are not present? We have defined Na for a few specific cases, no, like non-diffusing B, then equimolar, and then unequimolar. Okay. So now what if that what if like if these cases are not there, like these specific cases are not there, and some very complex situation is there. Okay. So we say that if our situation is very complex, if a system is very becoming very complex, very complicated, and we are not being able to define its concentration profile or the velocity profile properly, then we will not be able to derive it from the fundamental equation of mass transfer. Okay. So we said in that case we can write our Na as equals to mass transfer coefficient and into driving force. DF is driving force. Okay, and MTC is your mass transfer coefficient. Clear. So we said that for any complex situation where finding out the velocity profile or the concentration profile is very difficult, so in that case we can generalize a formula for our flux Na, that is equals to mass transfer coefficient into driving force. Now how this works? The Na you already know, it is mole per meter square second. This is the unit of your Na. Okay. Now what is our driving force? Now your driving force can be either concentration difference, like in this case it will be like Ca1 minus Ca2, or it can be partial pressure difference, for like Pa bar 1 minus Pa bar 2, or it can be mole fraction difference, because mole fraction ultimately if you just multiply it with total pressure it will give you your partial pressure only. So like this, like based on this also, and based on gaseous phase also, and based on liquid phase also. So like this, these are the driving forces. Now please understand, if these are the driving forces, and if you move a little bit forward, then our Na we can write it as mass transfer coefficient is, suppose we are taking the driving force as concentration, so Ca1 minus Ca2, and our Na unit we already know that mole per meter square second. So then we can just use our unit balance and find out what is the unit of the concentration. It will be mole per meter cube. So in that case, this will get cancelled. This mole will get cancelled, and we will get this unit as meter per second, isn't it? Because meter will get cancelled, and we will get second. Clear? So if the driving force is concentration difference, if the driving force is your concentration difference, or we can also denote it by delta Ca. In that case, our mass transfer coefficient will have unit of meter per second, and we just represent it by Kc. Okay, we represent it by Kc. Nothing, just concentration, so Kc. Clear? Now, for example, suppose you want to you say that no, I want to use my driving force as our partial pressure difference. Okay, so let us take Pa bar minus Pa2. So this again will be mole per meter square second. Unit of mass transfer coefficient is unknown. What is this partial pressure unit? Partial pressure unit will be Pascal. Okay, Pascal or bar, anything. Now directly our mass transfer coefficient unit will be mole per meter square per second per Pascal. Clear? So like this you can directly find it. Okay. Yeah, so it's clear now. My internet just got turned off. No problem. Okay. Yeah. So so we can write our flux as, please see here, we can write it as Kc into Ca1 minus Ca2. We can write it as Kg into Pa bar 1 minus Pa bar 2. We can write it as Ky into Ya1 minus Ya2. And we can also write it as Kx into Xa1 minus Xa2. where your Kc, Kg, Ky, Kxs, what are these? These are just those things like the mass transfer coefficient for the respective driving forces. Like if the driving forces is your concentration difference, then Kc. For partial pressure difference, Kg. For mole fraction for gaseous phase, Ky. For liquid phase, Kx. Okay, like this. So this is the format. So now one more thing we can do. One more thing we can do. What you can do is what you can do is you already know the general formula, no, for your non-diffusing B. For your non-diffusing B, you already know your general formula. That is your Na is equals to DAB into PT by RTZ and into suppose Ca1 minus Ca2 and divided by CBLM. This we have already seen yesterday. You already know this. And now you have defined that your Na will be is equals to Kc. Sorry. Na will be is equals to Kc and into Ca1 minus Ca2. So what we do is we just compare them, and we from here we can write that Kc is equals to DAB PT by RTZ CBLM for the case of non-diffusing B. Remember, this is only for the case of non-diffusing B. Okay, like the mass transfer coefficient for the case of diffusion of A through non-diffusing B, in case of concentration difference being our driving force, will be Kc. That is equals to DAB is equals to PT by DAB is equals to PT into Kc is equals to DAB into PT divided by RTZ into CBLM. Clear? Let us take partial pressure difference. So Na is equals to DAB into PT by RTZ. Okay, you can also write it as CT. No need to write this RTZ as because we are taking concentration difference, no. So you can write this as CT also instead of RTZ. You can directly write it as CT, and here no need to write Z RT. So this also like this also you can represent it. No worries. Right? This also you can represent it. No worries. Okay. Like this also. Like instead of writing it PTZ, you can denote it. Like if you write PTZ, then also it is not wrong. Okay. Because CT is nothing but PT by RT. Okay. Or you can directly write CT also. As because we are taking concentration, so let us write CT. Why to create any confusion? So from here, this will be PA bar 1 minus PA bar 2, and we said that in the denominator will be PBLM. And you already know that your Na is equals to Kg into PA bar 1 minus PA bar 2. So from here, your Kg will be is equals to DAB into PT by RTZ and PBLM. Don't forget to put your PBLM. Okay. So this will be the mass transfer coefficient for your non-diffusing B in case of partial pressure being our partial pressure difference being our driving force. Okay. So like this, you can derive it for your mole fraction in case of gaseous phase also, like delta Y, and for your delta X also, like in the same format you will be getting. Okay. So this was for your non-diffusing B. Now let us take a equimolar counter diffusion. Now let us little bit consider our equimolar counter diffusion. Equimolar counter diffusion. So if yesterday you went home and you followed the steps that I told you, if you yesterday you went home and you followed the steps that I told you, then what we discussed is Na is equals to Nt into Xa and plus Ja. And from here we said that for equimolar counter diffusion, our Na will be is equals to minus Nb. That means our Nt is equals to Na plus Nb, and which is nothing but equals to 0. So just put this in this equation. So this will be equals to 0. So our Na will be is equals to minus DAB. Ja is equals to nothing but minus DAB dou Ca by dou Z. Just integrate it. Again the same thing, as the diffusion area is constant, so our flux Na will also be constant. So just we will integrate this Z1 to Z2 and Ca1 to Ca2. From here you will be getting Na into Z2 minus Z1. That will be equals to minus DAB and into Ca2 minus Ca1. This minus and this we can take as common. This will be equals to DAB by Z and into Ca1 minus Ca2. Yes. If you want to convert this into your suppose partial pressure, then you can do it. Your Ca1 will be PA bar 1 by RT and your Ca2 will be PA bar 2 by RT. Just take RT common. So you will be getting DAB by RTZ into PA bar 1 minus PA bar 2. Okay. This will also be one formula for your Na. Suppose you want to write it in terms of mole fraction. So from here only you can write it DAB by Z. Just divide the take a CT common from the entire thing. Okay, take CT common. So from CA1 will be what? It will be XA1 into CT, and CA2 will be what? XA2 into CT. Just take CT common. You will be getting DAB by Z CT into XA1 minus XA2, and from here you can take PT common. So this will be Na is equals to DAB into PT by RTZ and into Ya1 minus Ya2. Okay. So all the Na formulas you have derived. All the Na formulas you have derived. This is in terms of mole fraction liquid phase. This is in terms of concentration difference. This is in terms of partial pressure difference, and this is in terms of mole fraction for gaseous phase. So again, four formulas you have got. For this is for the case of equimolar counter diffusion. Okay, so these formulas you can note it down, and again the same thing you can do. Again the same thing you can do it here also. Okay, what the same thing? What I'm talking about? What you can do is you can take your Na, that will be equals to, just one second. You can take your Na, that will be is equals to your let it be Kc dash for this thing, okay, and Ca1 minus Ca2. This is your mass transfer coefficient in case of equimolar counter diffusion, okay, and the general formula that we got was Dab by Z. This only we got, no? So from here your Kc dash will be directly equals to Dab by Z. This is the mass transfer coefficient in terms of for the specific case of equimolar counter diffusion, and when our concentration difference is our driving force. Clear? This thing is clear, no? Till here I hope it is clear, like it is very easy only, okay? These things are like very easy. So till here I think it is clear. So like this you can derive it for your, like, let it be Kg dash, Ky dash, Kx dash. You can derive it for them also. Okay, the same way, just compare it, and like we did it in case of non-diffusing B, no? Just compare it and find it out. So for that you can like that you can do it here also. Just compare it and find it out. Your Kc, K dash, Kg dash, Ky dash, Kx dash, all these things. Okay. So this was a very important concept. This was the concept of your mass transfer coefficient. Okay. This was a concept of your mass transfer coefficient. Okay. After this concept, one more concept comes. After this concept, one more concept comes. That is, what is the relation between all these mass transfer coefficients? Like suppose you have Kc, you have, oh, sorry, one second. Like I have to like a little, bold manner, because or else on the in the YouTube is not very, yeah. What is the relation between your Kc, Kg, Ky, Kx? What is the relation between all these things? Okay. So how to derive the relation between all these things? So let us see. So your flux Na, you can write it as Kc and into delta Ca. And this flux unit is same, no? It is mole per meter square second. Now this unit is same for all these cases. So you can directly write it Kg into delta Pa bar. You can also write it Ky into delta Ya. And you can write it Kx into delta Xa. We can write this, no, because the Na unit is not changing. Your Na unit is mole per meter square second only. Only the mass transfer coefficients and the driving force is changing. Now as the driving force is changing, the mass transfer coefficients unit is also changing, and it is balancing each other out to get the final unit as mole per meter square second. Clear? Now how to find out the relation between them? Just see here. How to do it? Just see here. So we have, let us take this and this. Okay. So Kc into delta Ca is equals to Kg and into delta Pa bar. Okay. Let us like convert this Ca into delta Pa. So how to convert this? Delta Ca will be is equals to delta Pa bar by RT, and that is equals to Kg into delta Pa bar. This delta Pa bar will cancel out, and you will be getting Kg is equals to Kc by RT. So this is the relation between your Kc and Kg. Okay. Now suppose you want to take this one and this one. So let us take it. So you will be getting kg into delta PA bar is equals to ky into delta YA. Okay. This you can write this as PT into delta YA. That will be is equals to ky into delta YA. So from your delta YA will cancel out. You will be getting kg into total pressure, and that is equals to ky. So you got the relation this also. Okay. Now just you try to remember one single equation. That is your Kc by RT is equals to your Kg, and this Kg is also equals to your Ky by total pressure. Sorry, by total pressure. Okay, because from here your Kg will be is equals to Ky by total pressure. Okay. Now if you want to write it in terms of Xa, like Kx also, so nothing. For that, what you have to do? Just let us take these two. Like, just find out the relation between this and this. Okay. So your Kc into delta Ca will be is equals to Kx into delta Xa. That will be just Kc into Ct into delta Xa, and that is equals to Kx into delta Xa. Delta Xa will cancel out. Our Kc will be is equals to Kx by Ct. So in this equation, just add one more line. It is Kx by Ct. Now you have an entire equation. You just any two relations you want to find out, you take those two terms. You're getting it what I'm saying? Like suppose you want to find out the relation between Kx and Ky. So what will be the relation? Kx by Ct will be equals to Ky by Pt. Suppose you want to find out the relation between your Kc and Ky. So Kc by Rt will be equals to Ky by Pt. Suppose you want to find out the relation between Kg and Kx. So Kx by Ct will be equals to Kg. Suppose you want to find the relation between your Kc and Ky. Sorry, Kc and Kg. So Kc by Rt will be equals to your Kg. Clear? Kg. This is Kg. So like this is also a very important concept. There is the relation between the different mass transfer coefficients. Okay. So with this our mass transfer coefficient is almost like over only. If like this till here you have understood, then it is okay. Till here we have done no. Till here I guess we have cleared no. No problem must be there. Okay. Then after this, one more concept is there, that is your dimensionless number. Like I hope you are understanding this. Just understand. No need to make notes now. I'll share you the PDF afterwards. Okay. Then you can make a proper notes. And we are covering it in a very fast way. Like not in very much that we cannot go to in the very much details like in the derivations and all. So that's why just try to understand it. Nothing we have done. It's very easy. Okay. What I said is that mass transfer coefficient is nothing but we have defined as because finding out Na was becoming a little complex other than specific situations. Like if you have specific case, specific situation, then it is okay. Like non-diffusing B, equimolar counter diffusion, unequimolar counter diffusion, all these things. If we are getting these cases, it is okay. We are deriving it. But suppose we don't get these specific cases. We have some complex situation, some unseen situation. So how to define the flux? We said that we can define the flux as flux is equals to mass transfer coefficient into driving force. Okay, very good. Now, what can be the possible driving forces? This can be concentration difference, partial pressure difference, or your mole fraction difference. Okay, very good. Now, after this, we said that okay, as the unit of the flux is like mole per meter square second only, like the unit of the flux will be constant only. So, based on the driving force unit, our mass transfer coefficient unit will be decided. So, we said that okay, the unit of the like mass transfer coefficient for Kc when the concentration difference is your driving force will be meter per second. For partial pressure it will be like this, for Xa and Ya it will be like this. Okay, then we said that we can do one more thing, that we already have the flux formulas for our non-diffusing B and equimolar counter diffusion. So if we have the flux formula, so let us compare the flux formulas and find out the mass transfer coefficient for these specific cases. Okay, just for these specific cases. So we have found out that also. We have found out here also. Like yesterday we didn't do this derivation, so I like wanted you people to do it on your own. So if you have if you have done it on your own, then you can check it from here. If you have not done, then you just write it down. Okay. So like this, we have found out the mass transfer coefficients, individual mass transfer coefficient for these specific cases also. Then we said that another important part is that what is the relation between these different mass transfer coefficients. So then we saw that how to find out the relation between these different mass transfer coefficients. Okay. Now after this, the next topic that we will be starting is our dimensionless number. Today we have to complete it, like dimensionless numbers also, and adsorption and strip, like not sorry, adsorption also, adsorption, not absorption and stripping, adsorption. Then we will solve these questions on your Sunday. Okay, and tomorrow there will be no class. Okay, chalo. So where were we? We were doing dimensionless number. Yeah. So dimensionless numbers. Let us cover it in a very fast way. Okay. Like only one, two, or two things are important here. So those things only we will focus. Other than that, we will just look into formulas. Okay. Okay, the first dimensionless number is Reynolds number. You have been doing it from your childhood only. Reynolds number, that is equals to rho Vd divided by mu. The definition and all these things, inertial force by like viscous force by initial force, inertial force by viscous force. All these things you have done it. Like these derivations you will find it anywhere. Okay, so no need to go into the derivations now. Let us just understand what is the importance for this dimensionless number in mass transfer subject. Okay, so first there is Reynolds number, then you have Schmidt number. This we define it as mu by rho dab. Okay, then we have Sherwood number, that is equals to your kc into lc by dab, where lc is your characteristic length. Okay. Then we have wait 1 second. Yeah, we have Stanton number. This is your known as Stanton number. Stanton number. Okay, this is equals to your Sherwood number divided by Reynolds number into Schmidt number. Okay, so this will just come out as kc by v average, where v average is your average velocity. Okay, then we have Peclet number, and that will be is equals to your Reynolds number into your Schmidt number. Okay, so these things are there. Everything like the physical for these things you will find it in any book and everything. Okay, like Reynolds number is equals to inertia force by viscous force. Schmidt number is equals to your like क्या बोलते momentum diffusivity divided by your mass diffusivity. Okay, all these things. So these things you will be able to find it out. No problem in that. And this dimensionless numbers, it is involved in your heat transfer also. So the what is the relation, like all these things are in correct format. Okay, like in case of in place of Schmidt number, in heat transfer we use Prandtl number. Okay, in place of Sherwood number, in heat transfer we use that number, Nusselt number. And Stanton number, this is for mass transfer. That's why we have written it STM. You can also write it for heat transfer. For heat transfer, this will just become STH. Okay, and in that case it will be Nusselt number divided by Reynolds number into Prandtl number. Okay, like this we will be defining it. So Nusselt number is HLC by K, Reynolds number is rho V, let it be LC by mu, and your Prandtl number is mu by mu Cp by rho. Mu Cp by rho, I guess. No, I forgot it. What is, yeah, mu Cp by rho only, I guess. So mu will cancel out, LC will cancel out, rho will cancel out. So we will be getting H by K V Cp. It must be rho VCP. It is mu Cp by K. Yeah. It is mu Cp by K. Sorry, I just forgot it. Okay, so I will also take your session. So like I will just like once our crash course is over, no, or once 2-3 subjects are over, no, I will just tell you a trick to like revise. Okay, because revision is very important. Oh, again, I have written the wrong thing only. Because remembering this all the 12 subjects all together is very important. Okay, rho VCP. Yeah, so like this. Okay, like this is Stanton number for heat transfer. This is Stanton number for mass transfer. Okay, like if you put everything, like in place of Schmidt number, we are having Prandtl number for heat transfer. Okay, that is equals to your mu Cp by K. In place of Sherwood number, we have Reynolds number. All these, sorry, so we have Nusselt number. So all these things are there. Okay. And Peclet number for mass transfer is defined as like this. For heat transfer, Peclet number will be Reynolds number into your Prandtl number. Okay. So like this, we will be doing this. So when we will doing heat transfer, we will look into this. Now let us not waste time. Let us complete it today. Okay. So dimensionless numbers are this. So what is the significance of these dimensionless numbers? It is that we have some certain analogies. We have certain analogies. Okay. Based on that analogies, suppose what are the analogies? Suppose like Sherwood number, you can write it as some constant k plus c into re to the power m and sc to the power n. Okay, like this. Like you have no that your Nusselt number is equal to 0.664 into your Reynolds number to the power 0.8 and Prandtl number to the power 0.3. Okay, these things are there, no? So like based on these things only, like in mass transfer also you have these things, but the derivations and all are not required. You just remember the form. Okay, so like this. And always remember that for sphere, this k value is equals to 2. For sphere, this k value is equals to 2. Okay. And suppose the medium is stagnant. Suppose you have a stagnant medium. You will find PYQs on this formula. Too many PYQs you will find on this formula. Okay, it is very important. Okay, so for stagnant medium. Now for stagnant medium, you know that your velocity will be equals to 0. This is your velocity. So if your medium is stagnant means suppose you have an naphthalene ball, you have hanged it in the air, and the air around it is stagnant. It is not moving. So if the air is not moving, air is stagnant, that means the velocity of the air is 0. If the velocity of the air is 0, then your Reynolds number will be equals to 0. If Reynolds number is equals to 0, that means your Sherwood number will be equals to k. That is equals to a constant. For sphere, it will be equals to 2. If it is not sphere also, suppose it is not sphere, it is some other shape, it is a cylinder like this. Still, the Reynolds number will be equals to 0 only. Your Sherwood number will be just be equals to some constant k. Okay, this k value might be it is given in the question. Okay. So why we use this concept of Sherwood number? Please understand. In heat transfer, why we use Nusselt number to find out our heat transfer coefficient. So for in mass transfer, why we will be using our this Sherwood number to find out our mass transfer coefficient. So this is Kc into Lc by DAB. This will be is equals to, this is only our Sherwood number, no? So this will be is equals to our K. So from here you can find out our Kc. Lc is nothing but our like what to say, characteristic length. Characteristic length. Detail of the characteristic length we will cover in your that thing. What to say it is heat transfer and your fluid mechanics. Now in mass transfer not much is required. In mass transfer just you remember this, that if it is a sphere, generally in mass transfer we deal with sphere. Okay, so if it is a sphere, then your characteristic length is nothing but your diameter. Okay, if it is a sphere, then your characteristic length is nothing but your diameter. Okay, so this was one analogy. We have two more analogies. This thing is clear, no? We just said that our Sherwood number we can write it as k plus some constant c, rd to the power m and sc to the power n, where m, n, c are all constants. Okay. So we say that for sphere our k value will be equals to 2. Okay, very good. And we also say that if it is a stagnant medium, then velocity will be equals to 0. If velocity is equals to 0, then Reynolds number will also be equals to 0. And if Reynolds number equals to 0, then our Sherwood number will just be equals to k, which is a constant. And for sphere, the constant value is 2. And also the characteristic length for sphere is equals to diameter. Okay, so this much you remember, it's enough. Okay, you can find out the PYQs. You will find two or three PYQs based on just simple this concept only. Okay, so this was one analogy. One more analogy is there, this analogy I will just write it down here. However, this you can understand better after we complete our fluid mechanics. Like after we complete fluid mechanics, no, then these two analogies you will understand it better. What are the analogies? The first one is known as Chilton Colburn. What is the spelling of Colburn? I check the spelling and all. Okay, spelling I don't remember. Chilton Colburn analogy. So what is Chilton Colburn analogy? It is said that you can write your JD or JM like of like for mass transfer coefficient. Okay, this will be is equals. This is known as your J factor. Okay, this is known as your J factor for mass transfer. This is equals to your Stanton number for mass transfer and into SC to the power 2 by 3. And this Jm is equals to your friction factor divided by 2. Now, what is this friction factor? If you know already, then it is good. But or else this friction factor we will be covering in your fluid mechanics. Okay. So directly you can find it like this. Okay. Now directly you know that your Stanton number is what? Your Stanton number is Sherwood number divided by Reynolds number into your Schmidt number. So you can put the value of this Stanton number here, and you can put the Schmidt number here also. So this is your J factor. This is known as your Chilton-Colbert analogy. Okay. One more analogy is there, that is known as your Reynolds analogy. So what Reynolds said is that this Jm will be equals to your STM and into SC to the power 2 by 3. The same thing he said, same thing. But in this case, he said that our Schmidt number must be equals to 1. So if Schmidt number equals to 1, then this will just become Sherwood number by Reynolds number. Okay, F by 2. This is our Jm. Clear? This thing is clear, no? So this is for mass transfer. What if suppose you want to write it for heat transfer? So the same thing, write it just JH, Stanton number for heat transfer, and instead of Schmidt number, you write Prandtl number. Same thing for here. So suppose you want to write it for like heat transfer, so JH, STH, and into PR to the power 2 by 3, and just instead of SC to the power SC equals to 1, your PR will be equals to 1 for heat transfer. Okay. So these two analogies are there. So I hope these two analogies are clear. Okay, nothing is there, just this formula. You just remember this formula. Okay, this Jm is known as your J factor. Somewhere it is written as JD also. For heat transfer, it is written as JH also. Okay, why we use this? So that we can relate our friction factor with our mass transfer coefficient. Please remember these dimensionless numbers we have defined so that we can find out our mass transfer coefficient, our unknown mass transfer coefficient easily. Okay, the main aim of using this dimensionless number like this, no one will be telling you. Wait 1 second, I'll just write it in detail. This is the main aim of using the dimensionless number, is to find out your mass transfer coefficient. Okay, that what is our mass transfer coefficient? Clear? And for like this, you can find out your mass transfer coefficient. Okay, now suppose you want to find out a relation between your mass transfer coefficient and your friction factor, or you want to find out the relation between your heat transfer coefficient and your friction factor. So in that case, we use our Chilton-Colbert analogy and our Reynolds analogy. Clear? There is one numerical also, we will solve it on Sunday based on this. Like, it is not a gate PYQ. In gate, questions from this formula has came. It is very important formula. This formula has came. This formula is also questions has came. You can directly find out. Okay. So this was all about our dimensionless numbers. Like, we have covered it in very brief, but still, like, this much that we have covered is more than enough. If you have understood this much and remember this much, it will be more than enough for you. Just solve the questions based on this and we will be well to do. Okay. So with this, probably our diffusion is over. Okay. The next topic, that is our two film theory, and that we will cover under your, what to say, that we can cover under your absorption and stripping. Okay. Other than this, some theories of mass transfer are there. Other theories like film theory, your penetration theory, and your surface renewal theory. So I'll just write down what is important part. The derivation and all these things, so we cannot go. Because you are understanding only, like in 12 hours we are going to cover the entire subject. Like, only how much times? I think 2.5 months are left. So if we go to like complete each subject in very detail, it will not be possible. Like, nothing magic can happen, no. But still, what is the takeaway? What is the important thing? I'll just write it down. If you remember that, I hope you will be able to solve the questions also. Okay. So please understand. So put your heading as not theories of mass transfer. No need to put heading, like you can make the notes later on. Just understand theories of mass transfer. So the first theory is film theory. Okay, it was given by 1923. It was given by Whitman. Okay, okay. It is based on steady state mass transfer and Fick's first law of diffusion. Okay, what it states? What it states? It just states that our Kc will be is equals to dAb by delta, or you can directly say that Kc is directly proportional to dAb. That is our mass transfer coefficient when our concentration difference is our driving force. This Kc will be is equals to dAb by delta, where delta is nothing but your film thickness. Where delta is nothing but your film thickness. Okay, like this. Like what is the takeaway? I will just okay. Like suppose you have here, no, so like this, suppose this thing is happening. Okay, this is one concentration and this is one concentration. Okay, like this we will be doing in the two film theory, but still, and let this be thickness delta. Okay, so here mass transfer is happening, no, so mass transfer happening, so we will have some mass transfer coefficient, and let the diffusivity be dAb. Okay, let this be bulk A, not bulk A, like some bulk liquid, like let it be bulk liquid. Okay, and this side let it be bulk gas, and let our solute be A. So our solute A is diffusing from bulk gas to bulk liquid, like a basic concept of our absorption. In absorption, what happens? The solute get transferred from gas to liquid. Okay. For example, I just give you an example. For example, suppose you have air plus ammonia mixture. Suppose you are having air plus ammonia mixture. Okay. So air plus ammonia mixture you are having, and what you do is that you use your liquid, that is nothing but your water, H2O. Okay. Now, if you put them in a absorption column, what is going to happen is that this air plus ammonia mixture we will feed it from here, and this clear liquid H2O we will feed it from here. And what is going to happen is that this solute, let NH3 be the solute A, this solute it will get transferred from this gas, that is your air plus ammonia mixture, that is gaseous phase, to it will dissolve in the liquid. Okay, and from here we will get liquid along with ammonia, like water like ammonia will dissolve in water, so for here we will get ammonia dissolved in water, and from here we will get clear air. Okay, so this is the basic idea. This is the basic idea of your absorption. Okay, so separation techniques like mass transfer, no, like the basic application of your mass transfer in all the industries is separation techniques. Mass transfer is separation techniques. So in most of the cases, what is going to happen is that in most of the cases, wait 1 second. Yeah, let me tell you this thing is important. In most of the cases, what is going to happening is that, like, why we learn mass transfer, the main application of mass transfer is your separation techniques. Okay, so in most of the cases, what is going to happen is that you are going to have a mixture of A plus B, and you apply a you allow a third component C, such that this C will take away our B and we will get A. Getting it? No, you initially you have a mixture of A plus B, you add a third component C, such that this C will not have any involvement with A, it will just take away B and we will get B plus C. Clear? For example, just now the example that I said, that NH3 plus air, NH3 is your let B, like the solute, this is your solute, and air is your component A. You add C, this C in this case was H2O. So what H2O did? It took away ammonia, that is our NH3 plus H2O we got, and from here we get clear air. Okay, so this is an example of gas liquid separation. Suppose you are having what to say, suppose a beaker is there and color is there, color plus water, color plus water is there. Okay, this color is your solute B and this water is your carrier, that is A. So what you add? You add with it activated carbon. You must have heard activated carbon. Activated carbon, what it does? It takes away the color. So you get B plus C, and then you are left with clear water. That is your A. Okay. One more thing. One more example. See here. In car, you use your the aerosols. No, in the car for removing the spray. Those things you don't use the aerosol. Like in the dashboard, you keep it. Everybody will be knowing only. Like this, it is there, and some smell is good. Smell is coming, or it is taking away the foul smell. So what is the basic example? Like what is the basic idea behind that? We have smell plus air. Okay, smell is your solute and air is your carrier, and you add your silica gel. Silica gel, these aerosols are what, once just remove it and take it in your hand. So these aerosols are your silica gel. This is your C, so this will take away the smell. So you get B plus C and you get clear air or smell free air. Okay, so like this, the basic idea is like this. Okay, so this is the example of your adsorption. Okay, this is also adsorption. This is solid liquid and this is solid gas. Okay, this is your gas liquid operation. Okay, absorption and stripping also. So what is stripping? Stripping is just opposite of the absorption. Like in absorption, what is happening? Your solute is getting transferred from, in absorption, what is happening? Your solute is getting transferred from your liquid to, your gas to liquid. And in stripping, what is going to happen? In stripping, it will transfer from liquid to gas. Okay. We will take an example like when we cover absorption and stripping on Monday. Don't be worried. Okay, so this is the basic idea. This is the basic idea of your mass transfer. So these are nothing, just separation techniques. Separation techniques. Your distillation, extraction, okay, everything, drying, everything is a like separation technique. In drying, what you do? In drying, you just have wet solid. In drying, which you just have wet solid. Wet solid means solid plus some water, H2, and you add heat. You add heat there. This heat will take away the water, and you get dry solid. Okay. All these things are separation techniques. Okay, chalo, enough. We are wasting time. Like this, we will not be able to complete. Okay, so this is your film theory. After this, so film theory, what things you have to remember? You have to remember that it is based on steady state mass transfer. It is taken from Fick's first law of diffusion. It is important for this. And like Kc, that is the mass transfer coefficient, will be is equals to dAb by delta. And from this equation only, you can directly say that our Kc will be directly proportional to dAb. Okay. The second is penetration theory. What is penetration theory? What things you have to remember? Just in very short, it is unsteady state mass transfer and Fick's second law. Fick's second law is valid here. Okay, and here you get that your Kc average will be is equals to root under 4 dAb divided by pi Tc. That is equals to 2 root under dAb by pi Tc. You just remember the formula now. Everything like deriving this is not possible. I'll just tell you the idea still. Okay, and from here you can write that Kc is directly proportional to root under dAb. Okay. In penetration theory, what we do is that we say that we are having bubbles. Okay. So these bubbles are rising. These bubbles are rising, and like mass transfer is happening. Okay, like with surrounding fluid is there, so mass transfer is happening. So what we assume is that this Tc is the contact time. So what we say is that the contact time for each bubble is same. Like you can take the example, no, in the distillation tower. Like suppose this is the distillation tower, no. So in distillation tower, what happens? Please understand. In distillation tower, your liquid comes from the top. Okay, like from here, suppose liquid comes to this tray. So this tray will be full of liquid. Okay, and once it reaches above the weir height, it will again flow down, and another trays are there. Okay, your gas will flow from here. Okay, like from here, your gas will flow. So sieves are there. You know different types of trays, bubble cap tray, sieve tray, all these things. So sieves are there. From here, gas will bubble through the liquid. As gas bubbles through the liquid, so contact will happen between liquid and gas, and your distillation will occur or mass transfer will occur. Okay, like the more volatile component will go from gaseous the more volatile component will go from liquid phase to gaseous phase, and the less volatile component will go from gaseous phase to liquid phase. So from the bottom, the liquid that we get is rich in your low volatile component, and from the top, the gas that we get is rich in more volatile component. Then we will send it to a condenser, and then we will get our distillate. If we want, we can put reflux. This we can directly put it into the reboiler. From the reboiler, we will get our residue, and we can put some reboiler like boil up vapor inside. Okay, so this is these things we will do in distillation. Okay, so what I'm understanding, we're trying to make you understand now. So suppose this is a tray. Here it is a liquid pool is formed. This blue color blue pool, no, it is known as the liquid pool. So from here, the gas will bubble through the liquid, contact will happen, and mass transfer will occur. Okay, so what we assume is that the contact time, like suppose this is a liquid pool. Suppose this is a liquid pool. Okay, just for example. So gas will bubble through it in this, like in forms of bubble. Okay. So what we say is that the contact time for each of the bubble, that is the time for contact between the liquid and, like, for how much time this bubble, like this bubble will form here, then it will rise like this, and here it will burst. Okay, and then again it will travel. So this time, the contact time, we take it as TC. Okay, this contact time, we take it as TC. And so for penetration theory, we say that the contact time for each of the bubble is same. Okay, like all the bubbles will have the same contact time. So that is the biggest like assumption we have taken, and this assumption is not correct. Okay, like these things is not, all the bubbles cannot have the same contact time. So that is your TC. This TC, no, this is your contact time. So I hope now you have understood the concept of your contact time. Like what is your contact time? Okay. So what are the takeaways? The takeaway is that you remember the general formula: Kc average is equals to root under 4 DAB by pi Tc, and Kc is directly proportional to root under DAB. Okay, this much you remember, it's enough. The third is surface renewal. Surface renewal theory. Here also these two assumptions are same as here also, and here you Kc is equals to root under DAB into S, and you can write Kc directly proportional to root under DAB. Okay, and S is your surface renewal rate. And its unit is second inverse, okay, or time inverse, generally second inverse. Okay, and here also Kc is directly proportional to root under DAB. Okay, with this just remember one more thing, that is your boundary layer, concentration boundary layer. Okay, for heat transfer we have thermal boundary layer, for fluid mechanics we have like what to say it, fluid boundary layer, and for mass transfer we have concentration boundary layer. So boundary layer, it is Kc directly proportional to DAB to the power 2 by 3. So this formula you just remember, this much is enough. Okay, yeah, so I think this much if you remember, like till today, this much, these are the theories of your this thing. Two film theory is there, but that we will cover in our that only, like interface mass transfer two film theory, and we will then go to into absorption and stripping, that we will start from Monday. So till here whatever concepts we have covered, we will solve questions based on this on your Sunday. Okay, tomorrow is your holiday, so tomorrow you just try to revise, you make the notes. If you just want to revise it once, you just revise it. Okay, and then Sunday we will solve the questions, and from Monday we will start our uh, absorption and stripping and your like, yeah, absorption and stripping. And before that we will look into what is interface mass transfer. Interface mass transfer means nothing, just here we saw the example of the absorption column. Now, so what is happening, gas and liquid mass transfer is happening. So two phases are involved, gas and liquid. So this is known as your interface mass transfer. Okay, so I hope today's class is clear to you. Today we basically focused on mass transfer coefficients. We derived the formulas for your equimolar counter diffusion, and then we derived the relation between different mass transfer coefficients. Then we looked into dimensionless numbers, and we said that the basic idea of using dimensionless numbers is to find out our mass transfer coefficient. We looked into three analogies. The first analogy was to find out our mass transfer coefficient, and the second two analogies is to find the relation between friction factor and mass transfer coefficient. Okay, and then we looked into theories of mass transfer. I hope till this much it is over. Okay, so next we will start. We will meet Sunday. Sunday we will meet with questions. The timing and all I will update it you. The timing of the Sunday classes I will update. Probably I will take class in the morning only. Okay. Chalo. So thank you. Let us end today's session. Okay, one more thing. The YouTube videos, no, like the videos of the first two classes have been uploaded in the YouTube. So you can share it with your friends, so that if they want to join, they can just have a demo and they can join it. Okay. Yeah, that's all. So thank you. You revise well. Try to revise. If you are already preparing, so go on with your preparation. Okay, if you are taking this as the main preparation, like this crash course as your main preparation, if you are taking, then you just make proper notes from the crash course. I will send you the PDF today also. So you just make a proper note of the with the crash course, and then you follow the questions. Like Sunday we will solve the questions, and based on that you solve other PYQs that are present. Sure. So thank you.